All right, I want to welcome you to Waterproofing Details of Connections for Adjacent Precast Concrete Box Beam Bridges, brought to you by Anil Patnick. Please mute your computers, and I ask that you hold your questions until the end. With that, Anil, go ahead.
Thank you, Jill. All right, good morning. My name is Anil Patnaik, and I am a professor in structural engineering at the University of Akron. My background is in structural design and materials, mostly structural engineering materials. So I do a lot of research on materials and structural aspects related to structural engineering. The other presenters who are not here, but Dr. Habu and Dr. Al-Monbi, they are my former students. Both of them earned their PhDs from this project. So they have done most of the work in this project. So first of all, I would like to acknowledge a lot of support I got from ODOT SMEs. Number one, the funding came from Ohio Department of Transportation, obviously. And also some of the funding was provided by ORIL. So initially this project was started by ODOT, but later on, after about 6 months, ORIL showed some interest and they provided part of funding for this project. Dr. Khalifa, Mr. Jim Welter, and Mr. Riccardi, they were very closely associated with this project. They provided lots of guidance and a lot of information related to ODOT practices. And then Perry, Mr. Riccardi, actually provided the bridges for field evaluation and also for actual implementation of the project. My graduate students, the two of them who earned their PhD, did a lot of work, and they got a lot of help from their fellow graduate students who were working on other projects, but they helped in the lab work and field work and stuff like that. So today's presentation is organized into a few sections. The first section would be introduction. Most of you are probably familiar with this concept of box beam bridges, but I'll give a brief overview of what is normally done in Ohio. Factors affecting joint performance, we'll talk about it very briefly though. The primary focus of this project initially was on waterproofing materials and the performance of waterproofing materials. And then later on, we realized that the membrane performance is not necessarily the only problem. So we looked at joint performance of keyway joints, and then we did finite element analysis to support what we were doing. Then we also looked at many field practices and some practical issues. And then I will also present a few details on implementation and conclusions. So a typical box beam bridge will have a series of boxes. So they're typically in ODOT standards. We tie three boxes together, and then there is an overlap of ties. Therefore, the goal is to ensure that all the box beams work together as a single unit. So the tie rods are 1-inch tie rods. They're not really post tension, but they are just snug tight. So snug tight tie rods will probably give us about 15 fifths of force for each tie rod. The spacing is about maximum spacing of these tie rods is 25 feet. So along the length of the box beams, it's the practice to provide tie rods at maximum spacing of 25 feet. And the joints here are created by providing some keyways in the on the sides of the precast concrete box beams. And later on, once the boxes are together, placed together, and then the tie rods are in place, the keyway recess is grouted with normal cementitious grout. That's the current practice. So in this slide, what you see is on the left-hand side, the top left-hand side, you see a typical cross-section of a box beam. So this is a precast, prestressed concrete box beam. And all these box beams are pre-tensioned. And on the sides, you will see, if this is an interior box, so on the sides, you will see keyway recess formed in the box beam itself. There are two depths of keyway recess here. This depth for most box beams is 4 inches. And for larger box beams, deeper box beams, it's about 6 inches. And what I should have provided an enlarged view of this, but here, the distance from here to here, which is the recess of the keyway, is 3/4 of an inch. With the top opening here, we have 3/8 of an inch on one side, so two sides will give us 3/8 times 2, that's 3/4 of an inch. So what we have is an opening at the top. If the box beams are placed side by side, and if the alignment is perfect, then technically or theoretically, it should give us 3/4 of an inch recess to place the grout in the recess. That's the way it should be, or it could be. Provided you have perfect alignment and there is no mismatch, things like that. And the camber is perfect on both sides, then you get 3/4 of an inch recess to fill the grout. Anchor rods are generally meant to tie the beams together, and they are tied before the grouting, and 15 cubes of force is what keeps the beams together, and the grout itself is more or less a filler. We're not sure what kind of structural role the grout has, but we will look at those, look at the actual contribution of grout in terms of shear transfer later on in this presentation. So once the boxes are in place, the grouting is done, and then a waterproofing membrane is placed on top of the deck surface, and 1.5 inch asphalt concrete is placed on top. So the assumption is the waterproofing membrane will keep the water away from the joints, and if it doesn't, what you see here is likely to happen. On the bottom left side, you see a picture of water leaking through the joint, and this is one of the pictures I got from Pennsylvania DOT reports. And once the water and moisture penetrates the joints, you can expect significant amount of corrosion, particularly in locations where we have chloride penetration. And to the extent that the strands do detach and they do hang, and it can look quite unattractive, so to speak. So it's these boxes still maintain some amount of structural integrity, But we all know that any pre-stressed concrete is good enough as long as the strands are intact. So the primary objective of this study was to understand the performance of the joint behavior. And initially the focus was mainly on waterproofing of the joints, and cracking and differential deflection were also studied they were required to be studied so as to identify the problem of water leakage. And then once the study was complete, we had to come up with some kind of preventive measures. So the three major factors we studied in this project were membrane performance, joint performance, and some practical issues, including implementation. Just a brief mention, it's not even a review, but it's a mention of other people's work. The practices in other DOTs are slightly different from what we use here in Ohio. And some of the DOTs actually use post-tensioning with very large post-tensioning force. Just to remind ourselves, ODOT uses just snug tight anchor rods or anchor bars. And snug tight anchor bars will give us about 15 kips and over a length of 25 feet. That translates to 0.6 kips per linear foot of so-called clamping force, provided the force is transmitted over 25 feet. So if it is transferred over 25 feet, then you get an average of 0.6 kips per linear foot. But in other DOTs, they have moved away from just snug tight anchor rods, and they use post tensioning, and the amount of post tensioning also varied considerably, and it can be as much as 12 kips per linear foot in some cases. And what we found from our literature review, this comes from a PCI state-of-the-art report, and a lot of DOTs are using unbonded post-tensioning strands, PT strands, post-tension strands. Some are post-tension bars, but primarily strands and bars are the most common tying mechanisms that others are using. On the right-hand side, I think this comes from Michigan DOT report. Very interesting observation here is they did some finite element analysis for box beams. They combined 3 of them, and then they used tying force as one of the loads on the finite element model. And this on the right hand bottom side, in the bottom picture here, what you see is the tie force along the length of the beam. So on the top you have cross section, on the bottom you have longitudinal section, which is along the length of the beam. And you see local peaks. These local peaks were determined from finite element analysis. And what you see is these peaks are really confined only to the diaphragm location. So in other words, our tie force, whatever we apply, is only effective over the stiff location, which is the diaphragm location, and that's generally about 12 inches or something like that. Depends on the detail we have. So all the tie force is concentrated close to the diaphragm. There are many other reports that have described research on box beam girders, but I won't go through all the details because there is a lot of material to be covered, and we documented the literature review in our report. Another thing that's interesting is quite early on, like more than 10, 15 years back, it has been recognized that the joint is a real problem, and many researchers studied the joint performance, and to the extent that for railroad bridges, they use two post-tension strands to tie together the boxes. And then there are many other mechanical attachments. I think Ohio University is doing some project on mechanical connection, which is very effective. And they use different types of joints, deeper joints, full depth joints, wider joints, different shapes, joints with different shapes, and of course the traditional joint with small depth keyway. So now we'll briefly outline the membrane performance. When we started this project, or even before we started this project, our focus was mainly on membrane performance. So we assumed, rightly or wrongly, that the membrane is the real problem, and the membrane is damaged, and that's the reason we have water leakage. So we tried to understand the membrane performance under many different loading conditions. What I'm going to describe in this section are very, very simple tests, but they are very effective in the sense we get the answers to our questions. So we did primarily 5 different types of tests. Tensile tests at different temperatures, the bond test, which is adhesion tests, differential deflection tests, punching tests, and tests to find out if there is any leakage at large differential deflections. So we picked 5 different membrane types, and 3 of them were not in ODOT QPL, and then 2 were from ODOT QPL. Some of them were self-adhesive type membranes that was specifically requested by ORIL to study self-adhesive type of type 2 membranes. So if successful, they could use that. And then others were the traditional membranes. And these 5 were picked based on a big list of about 30 membranes. And then we just picked the representative samples. So initially we started with tensile tests. We thought the membrane is actually rupturing under axial loading. And then we created simple tensile specimens, very 10-inch long specimens, 1 inch wide. And then we use some plates at the ends, and then we apply tension from the 2 sides. So what you see here on the left-hand side is load elongation curves. On the x-axis, you have elongation, and on the y-axis, there is load. What you'll see is the load carried by these membranes is very, very small. And there are 5 different membranes here. We looked at the effects of temperature from 70 degrees all the way to -40. And then we tested lots of samples. And what you'll see from this figure is all these 5 membranes were able to stretch as much as 1 inch, or in some cases more than 2 inches. So the key point or key finding from this test is that the membrane is able to stretch at least 1 inch without rupture. The next set of tests was bond test, adhesion test. So we created a simple, or we came up with a simple loading mechanism and made some test specimens. Even though the tests are very, very simple, what we found from here is the peel out strength of these membranes is very, very small. That means for a very small load, the membrane is able to peel off and all the bond is damaged at the interface. Of course, there are a couple of other findings. We said sealant and primer together performs better, but still there is very little bond. Then we tried to understand the membrane performance in terms of differential deflection. So if you see the figure at the bottom, you see we are trying to focus on the differential deflection of adjacent beams, and once the joint is damaged, then these beams are primarily acting as single units. They are not really acting together with adjacent beams. So once the joint is failed, we can expect the beams to have some differential deflection, and we thought maybe the membrane is being ruptured during those that type of differential deflection. So we created some simple specimens. We made some specimens and then we applied shear loading. You can see that. And what we found was the membrane is able to accommodate as much as 1 inch of differential deflection without rupture. So that's an interesting finding. We did not expect that. And many of the membranes failed without too much of, they were not detached. They were not really, they did not become two pieces. Some of them did, but in most cases, we were able to elongate or the differential deflection could be as much as 1 inch, or in some cases, it's greater than 1 inch before the membrane failed. And then our SMEs said that it's very important to understand the construction practices and how the contractors are actually not preparing the surface of the membrane adequately, and they're driving their heavy equipment and stuff like that. So we then came up with a simple punching test to figure out what kind of load will cause punching in these membranes. So my student came up with this mechanism whereby we have an electrical circuit here, and we have defined load applied through a small pointer, and anytime the pointer punches through the membrane, you will complete the circuit, and then that causes, that causes the it makes a sound, and then we are able to figure out when there is punching through the membrane. And what we found was the punching strength was very, very small, almost like 100 pounds. So even if an average person walks on the bridge, if the bridge has some debris, sharp edges, even we can create some kind of punching in the membrane. That's the finding from this test. The other test was we wanted to figure out at what differential deflection the actual water can pass through the membrane. So when does the leakage start? So for that we did a lot of trials, and finally we came up with this arrangement where we tie the membrane to a plastic to a plastic tube, and then we apply load over this 4-inch diameter steel plate. So there is a little bit of gap between the inside of the tube and the outside diameter of the steel plate. So when we apply load, this is the kind of deformation that we can expect or we got. And after the deformation or during the testing, we actually poured some water with dye to figure out at what differential deflection or differential deformation the water starts leaking. So as you can see, even after about 1 inch, 1.25 inch differential deflection, the membranes did not leak. So our initial assumption that the membrane is the problem and it's causing the water to leak through the joints is entirely false. So the membrane is able to accommodate significant amount of extensional elongation more than 1 inch. It can accommodate significant amount of differential deflection, and it can also prevent leakage even if there is 1 inch of differential deflection. So with that understanding, we switched our focus from the membranes to the joint performance. So in the joint performance test, we did a lot of keyway joint tests. Keyway joint tests, and then we were able to consider many factors, many variables in our joint tests with small specimens. And then the larger tests are time consuming and more expensive tests. Therefore, we try to understand the factors influencing joint performance with keyway joint tests, which are smaller tests. And then we actually downsized or down selected our variables to go to the next level, which is large beam tests. So beam assembly tests with symmetric loading, that's one type of test we performed in the study. Then we realized that once the beams are acting as single beams without any interference or any interaction from the adjacent beam, then the beams can also have torsional movement, or there can be torsional deformation. And therefore, we also looked at joints subjected to out of plane movement, which is very critical once the joint has really failed. So these are the types of tests we did. So the first type of test is simple specimen with different types of joints. We studied 4 different joints, and we studied many different grouting, 7 different grout materials. We looked at the bonding condition, that's the sandblast condition, as cast condition, clean condition, unclean condition, using bonding agent, without using bonding agent, using some kind of cement slurry and stuff like that. So there are many variables used in this joint tests. And then we did also we looked at the width of the joint. What you'll see here is this is our ODOT specified joint geometry, keyway geometry. First, of course, shallow beams. For deeper beams, we have 6-inch keyway depth, but in this case, it's 4-inch. And this was twice as much. So the width was increased by a factor of 2. And then we kept the same width as our ODOT width of the keyway, and then increased the depth. And in this set, we increased the width by a factor of 2, and also the depth was increased to 4. full depth. Okay, so like I said, these joint tests were screening tests, kind of screening tests, so we were able to down select our variables to give us more meaningful results. So what we found was, of course, what I did not show here is we also used tie rods. So tie rods, scale down tie rods to simulate the amount of clamping stress you can get from the actual tie rods, 1-inch tie rods. So we found that even a small amount of clamping force on the joints, perpendicular to the joint surface, will increase the shear transfer strength significantly. That's a very important observation we made. Deeper and wider joints definitely perform better than the shallow joints. I mean, that's common sense because we have a larger shear area, therefore deeper joints will provide some amount of increase in shear transfer strength. We looked at 7 different grouting options, and the traditional high strength concrete grout with number 8 aggregate gave us very good results in terms of shear transfer strength. So the traditional grout doesn't have coarse aggregate, it only has fine aggregates. And the grout material comes in bags of 50 pounds. They have an instruction on top of instruction on the bag, printed on the bag. So there is no control over what goes into that mix. But if we control our mix proportions and use number 8 aggregate, and we control our water cement ratio, and if we are able to get maybe 10,000 psi, which is very doable these days, 10,000 psi strength in maybe 3 to 7 days, we were able to improve the joint strength significantly. So what's the difficulty with the current grouts? This slide shows the difficulty we have in terms of the current grout. If you see the instructions on the grout bags, it comes in paper bags. On that, it says use 3/4 of water for 50 pounds of this grout. That's what it says. So we said, let's use 3/4 for 50 pounds. The workability you get is this. It's very, very stiff. The grout is so stiff that even in lab conditions, leave alone field conditions, even in lab conditions, it's impossible to place the grout with the amount of water they have specified in the instructions. It's not possible. And if you see any, I'll show you some pictures of the actual construction practices. The manufacturer says, just add water. That's what it says on the bag. So that's exactly what the contractor does. He just adds water, more and more water, in order to make it flowable. And it's understandable, because with this kind of workability, you cannot place the mortar in the very narrow opening of the longitudinal joint. We added a little bit more water. We said, let's use 4.5 quarts, and this is what you get. This is a spread test. Most of you are probably familiar with this. So we get 8-inch spread, which is slightly better than this, where you have 0 spread, but it's not really flowing grout. Then we added just a little bit of superplasticizing, 40 ml. Makes a big difference, almost 12 inches of spread. With the small cone, of course, not the big cone. Big cone will give you more spread. Then we added same 3/4 of water with 80 ml of super plasticizer, you can actually double the amount of spread. If you add 160 ml, which is a larger amount, we know that, but if we do, the grout really flows smoothly over a very large diameter. And to the extent that we ran out of grout from the cone, if we had more grout, it probably could have spread a little wider. So the two key points, takeaway points from this slide is the amount of water that is specified on those bags of ODOT approved grouts is not workable. You cannot place your grout in the small keyway joint with that kind of workability. Number two, even if we add a little bit of super plasticizer, we can make it really much better. So Perry actually asked us, what's the effect of this amount of water we add? Then our students went to the lab and they made some lots of specimens, three specimens for each data point. And they generated this relationship between water content on the x-axis and the compressive strength on the y-axis. We have 4 different curves, one for 1 day compressive strength, 3-day compressive strength, 7 days, and 28 days. 4 different curves, and for different amounts of water. What's interesting here is for the 1 day compressive strength, 3/4 of water, which is very difficult to work with, but in a lab we are able to control better, so we can make concrete with very low water cement ratio. So we got 4,000, which is not too bad. That's in a lab condition. But if you increase the water content as they do on the construction site, you can see the difference. This is 4,000, this is 900. That's a factor of almost 4.5. Every single strength curve is reduced by a factor of 3 or 4 if we add more water. So that's the problem, and that's the practical problem. Nobody has any bad intentions, but it's just a practical problem. You cannot place the grout with the amount of specified water. Then we try to understand what kind of stress conditions exist in the joints. So are they just functioning like fillers, or are the joints functioning in a way that we can consider as load transfer? And in order to understand the stress condition in the joints, my students did lots of finite element analysis, many different configurations, many load conditions and stuff like that. We did finite element analysis for 90-foot bridge, which is the longest bridge in the ODOT standard. Some intermediate length bridge, 60 feet length and 40-foot length. So we have 3 different spans, and then we used different keyway geometries, and then we came up with these stress profiles. So this is just showing an example of what we did. This is for a 40-foot span bridge. We applied wheel loads. Of course, as long as the load is uniform over all the beams, the beams are unlikely to deflect in a differential manner, so there may not be any differential deflection. Only the wheel loads are likely to cause differential deflection, so we just focused our attention on wheel loads. So we got our bending moment diagrams and stuff like that, and then we applied the loads in our finite element models. It's just a cross section of the finite element model. They are actually running, in this case, 40 feet. in length. So there are a couple of load cases that can cause problems in our on our joints. We are focused mostly on the joints. So if the wheel load is arranged in such a way that two boxes, adjacent boxes, are rotating away from each other, that will cause tension at the top. So that can be a critical load case because that's where the cracking will start. And then we can also have this kind of load configuration where the tension is at the bottom. So while you won't see the cracks on the top, the cracks at the bottom will reduce the depth of the joint that is effective in transferring the loads, and therefore it becomes more critical. So progressive development of cracks is a bad thing because we are assuming that we have 6 plus 3, let's say 7 inches of joint depth initially to start with, but as the cracks progress, our joint depth is reducing from 7 inches to maybe 3 inches or 4 inches or whatever that is. So we looked at these load conditions, and what we found was deeper keyways. What you see here are 4 curves. For load case 1 and load case 2, one causes tension at the top, the other one causes tension at the bottom. And we have a 7-inch deep keyway and 7-inch deep keyway. So that makes it 4 curves. And then we have this dotted line or broken line and the solid line. So the dotted line or broken line is for 7-inch deep keyway, and the solid line is for 11-inch keyway. So obviously the stresses, the tensile stresses are reduced by a significant margin if we increase the depth of the joint or the keyway depth is increased. So that's for 7 inches and 11 inches. So if we increase it from 7 to 11, we get substantial decrease in our tensile stresses. Same thing for tension at the bottom. So with that understanding, we designed our tests, and we focused on just 7 specimens here. But remember, these are very big specimens, 14 feet, 16 feet long specimens. We cast 3 different units with the keyways that we are testing, and then exactly those 3 units are cast separately. Then we put them together and then use tie rods to tie them together, just like we have in the standard specification. And for this, we have 3 specimens, and we have full depth joint, keyway joint, and this one has also full depth keyway joint with polymer grout. So polymer grout is considered to be upcoming grout. Many are using polymer grout for some special applications. So our SMEs suggested why not try that and see if there is any improvement. If the solution is as simple as just substituting the current grout with polymer grout, why not use it even if it costs a little bit more? So we tried polymer grout as well. But our study showed that the high strength concrete, which is readily available in all our ready-mix plants, is a equally good or very good grouting material. So we have some pictures here. I'll move on. So we have 3, sorry, not that fast. Sorry. So we have 3 units tied together with a tie rod, just like the specification tells us. I'm sorry, there's a roller here which is bothering me. Okay, so the tie rod is snug tightened, and we use a torque wrench to make sure we have exactly the tie force comparable with the 15 kip tie force we use in the field. And then we grouted the joints just like we are supposed to, but of course in a lab condition, which is more controlled condition. And then we tested these very long beams, or 16-foot beams, 14-foot beams. And then what we found was, without going into all the details, our high strength concrete with very good sandblasted surface is able to increase the joint shear strength by a large margin, maybe 6 or 7 compared to ODOT approved grout. So what we have here for ODOT approved grout is about 30, let's say 38 kips. And what we get for high strength concrete on the extreme right hand side is 275 kips. Big increase in shear transfer strength. At the time these tests were conducted, our SMEs and our research team, we felt that polymer grout is implementable because it mixes well and it can be placed without difficulty. And from these results, what we see is if we have a deeper keyway joint, of course, with twice the opening width compared to what we have in ODOT specification, we are able to place the grout better, and therefore we are able to get better strength. Okay, so high strength concrete grout work fine. What you have here is the surface of the keyway after the failure of the beams. With traditional ODOT approved grouts, there is almost no bond between the surface of the concrete precast, so-called precast concrete, and the grout, and these three elements detach from each other very easily. Whereas with high strength concrete grout, we are able to almost achieve monolithic condition, which is condition that you expect in case of cast in place concrete, which is very good. So my students actually detached these using jackhammers. A lot of effort went into this, and the actual failure occurred at the location of the stirrups. You can see the stirrup indents. So it did not fail at the joint, but it failed in the main concrete precast unit where the stirrups were located. So that's a very good performance. The next thing we did was we looked at the condition of these joints when there is out of plane movement. And for that, similarly, we looked at 3 different load cases. One, symmetric loads but causing tension at the top. The second one has symmetric loading but tension at the bottom. And this is a new load case where we apply load to only one unit, and this is quite possible once the joint is kind of, or the 2 beams are acting independent of each other. It's possible. And if the joint grout is holding them together, it's highly likely that the out of plane movement will cause tension or separation of the joint at the surface of the keyway. So once again, without going into too many details, we found that whenever we increase the depth of the keyway joint, theoretically, the finite element analysis tells us that the stresses are reduced by a large margin. And then we wanted to prove it or correlate or validate that information or the finding from the finite element analysis with actual tests. And we designed these simple test specimens. These specimens were not very long. We just made it 4 feet long. And then this test was kind of tricky in the sense we need to apply the desired amount of shear load and the movement, out of plane movement and they should be in proportion to each other in such a way that we are not increasing just the moment or just the shear, but they simultaneously are loaded to the same level with every increment of loading. That's what is challenging, and we did lots of analysis and got the combinations. The test setup looks something like this. We apply load here. You don't see a jack at the bottom, but we also apply another load from the bottom to make sure that the shear that's applied to the joint represents the actual stress condition in the bridge. And my students tested many specimens. Once again, high strength concrete grout performed the best. And from there, we got very good confidence in terms of what would make our joints perform better. So one of the first things we understood was the effect of tie rods. Tie rods are very important. At the same time, the tie rods we use currently in our specification may not be providing adequate clamping force. The keyway geometry is very crucial. By changing the keyway geometry, number one, we increase the width of the opening at the top, which will give us proper access into the keyway joint to place the grout. Very important. So the least thing we can do is to increase the width of the opening. So in practical terms, that will help us place grout better. And then deeper keyway joints, of course, many other researchers have done this research in the past. It has always proved that deeper joints are performing better. What we did in our work is simply restating what has already been understood by many others. But the type of grout that we used is simple high strength concrete grout with number 8 aggregate, which worked really well. Joint surface preparation, of course, the ODOT specifications clearly mention the type of joint preparation required. But at the same time, we cannot emphasize enough the joint surface preparation for the box beams. Very important. Somewhere we had to have some kind of check and balance to make sure that the joint surface is properly sandblasted and it is giving us good rough surface. This is kind of harsh. The current ODOT keyway geometry and grouts do not seem to be practical, unfortunately. So we came up with suitable modifications. I will show you those modifications in a minute. What we have in the next section is some details from old bridges, new bridge construction practices, and implementation. That's what I have, 3 sections. So here in District 3, Perry gave us this bridge that was being demolished, or it was being torn down. So our students went there and then removed the concrete and looked at the membrane condition. In many locations, we did not see any membrane. And the corrosion, which is shown here of the strands, is directly correlating with the locations where there is no waterproofing membrane. But remember, this is an old bridge, maybe 35 years back. ODOT practices have improved significantly over the last 35 years. So probably this is not happening anymore, but it is possible. And the second thing I'm showing you here is the practice, current practice. This is a bridge that was built maybe one year or 1.5 years back. And without telling the contractor, we just went there and we were just observing what they were doing. And then we were asking questions, explain to us what you are doing, things like that. So without telling them what we were doing, we just made some observations. And what they do is they actually add water until the grout is fully flowing. That's the way they see it. Okay, so they don't see the structural aspects of the grout, but they just look at grout as a filler material. So they just fill it and then keep going. And the bottom is sometimes not properly sealed. Therefore, you will see a lot of grout going into the stream. In this case, there is a stream below that. So it goes into the water. So that's a big problem. And then what we did was in one of the bridges, once again, Perry gave us this bridge in District 3. So here we measured the actual differential deflection between adjacent box beams for a bridge that's in service for a long time, and it's still in service. So we found that the differential deflection and separation of the beams was about 0.05 inch, which is not too bad if you look at it. So the differential deflection, vertical deflection is about 0.005 inch, which is about same as what the crack width limits are for reinforced concrete, about 0.005, 0.007. So it's not too bad. The horizontal movement is about 0.015 inch, which is not bad. So our membranes are able to bridge that kind of differential deflections and that kind of vertical or separation. So we got confidence that the membrane is not necessarily a problem in that kind of deflection. The next item was implementation. So what we did was we tried to implement all these findings in a project, and the simplest thing we can do is to increase the depth of the keyway and improve the increase the width of the opening here so we can actually place grout adequately, and also use high strength concrete grout instead of the traditional grout. So we did that, and of course, when we remember this is a pre-stressed concrete beam, so if you remove any area from material from the box, then you reduce the area, and therefore you have to change the amount of pre-stressing strands. So we did that. We did the design, and then we offered our drawings, and the PE actually stamped on it, which was good. So we increased the width of these keyway joints, and then we implemented this in actual bridge. One thing that really bothered the contractor was the amount of the strength gain that we are requesting. So he said, I don't want to do anything with your mixed design. We asked him, can you please at least, come up with your own mixed design and do a grout with 1,000 psi, 10,000 psi strength? No way, we're not going to do that. So they used our mixed design that we used in our lab, which worked out very well actually in the end. But he was very concerned about the flow. So we did some trial mixing and trial placement, and it worked out really, really well. You can see that. And the compressive strengths were really, really good. ODOT District 3, Michelle and others, they tested those cylinders. It worked out very, very well. And then on the bridge in Shelby, we actually implemented this grout. They went a little bit overboard. They made this very, very flowable, which is not necessarily what we expected, but they did that with super plasticizer, which is good. So it was really, really flowing to the extent that when they were filling this joint, we can see that the grout was flowing to the far end and to the adjacent joint really well. So the constructability was tested very well. And then after about 6 months of service, the bridge shows no cracks. Traditionally, you'll see cracks along the joint. So that's there are no cracks until this point. And what did the change order cost us? It's about $4,500, which is not too bad for a bridge of this size. 55 feet, that's what this bridge was. So steps needed for implementation. I need to wrap up in a few minutes, so I'll just quickly go through this. We need to look at, or at least Tim Keller and others in his group may want to look at considering the changes to the keyway geometry if possible, and if it is feasible, and if it is doable without much difficulty, we should at least consider that option. And Jim Welter actually suggested we make some changes to these items just to make sure they are compatible with what we are asking for. And of course, we cannot emphasize enough that the contractor needs to do his or her job as required in the specifications. That's a very important aspect. Of course, I have these sections because our guidelines say that, but in any case, we understand the expected benefits and risks and obstacles. I'll just move on. And then potential users, primarily ODOT and other DOTs. Cost of implementation, I already mentioned this, 4,500 is what we got for a 55 feet bridge with 7 joints, which is not bad. So in conclusion, what we found was membrane failure is not necessarily the culprit. So we came up with different options. Unfortunately, our ODOT current practices, particularly the width of the keyway joint, is very restrictive, and also the grout performance is questionable. So at least we need to look at those 2 aspects. And then we revised the keyway geometry. We used high strength concrete and better surface preparation, and strict enforcement of specifications will definitely improve the joint performance. And we believe that the recommended modifications are practical, achievable, and implementable. Okay, I think that's all I have for today. Thank you. I'll be happy to answer your questions. Yes, Tim.
Membrane is not causing the leakage. Is that fair statement?
The membrane is able, the question is, I stated in my presentation that membrane is not necessarily a problem. The question is the membrane causing the problem or causing the leakage?
No. So if membrane's not the issue, the amount of movement seems to be less than the membrane could accommodate.
That's right.
Yet they were leaking.
They were leaking, yes, that's correct.
So the membrane's not effective, the membrane's not aware. How is the water getting past the membrane?
Good question. How is the water going past the membrane? That's the question. There are 2 things. One is the membrane rupture can cause leakage. And what we have shown here in this work is that's not necessarily a problem. So the rupture of the membrane is probably not causing the problem. In our tests, we found that even 1 inch of differential deflection, 1 inch of tension is not causing any water leakage at the joint. But water may be seeping or passing through the underside of the membrane from somewhere else because the bond itself is not perfect. So the bond between the membrane and the deck is not adequate or good enough, and therefore water may be seeping from somewhere else. It's not necessarily because of differential movements of the beams itself. That's what we think. Perry, you want to?
So some of the projects that we went to review the contractor's work, the preparation for the topsoil beam was not very good at all. Many shards, contractors routinely would take paving equipment directly on top of the membrane, there may be aggregate on top of the membrane, and the construction practices really didn't do anything to protect the membrane. And one project where I saw the information, probably there were hundreds, if not even 1,000 penetrations through the membrane before the paving was even down. So we wasting money with membrane. Well, in that particular case, yeah, I would say so.
How would that be different than any other bridge we put up? Right? I mean, that's pretty standard practice.
Well, pave over it, like that, is that the same stuff? All I can say is that at least part of the problem is workmanship and the lack of attention to damaging the membrane during the paving operation. something else that we've noticed is that at times when our contractor is going to pave these membranes, on top of the membranes, that the membranes move a lot during the paving operation. And at the time, I never thought to ask just how much cure they gave before they got on it. You know, make sure the tank coat was appropriately cured. But I know that if there's any grade at all on the bridges, it can be very difficult. And these weren't even box bridges; these were just bridges that were bridges over the interstate that were overlaid. But it can be very difficult. All those membranes in place. That tank coat probably is.
One comment, two questions. The other comment is, a lot of times construction, contractors don't wait until the period for the tag, then they go over it and they look to membrane out. Question, the type 2 to the type 3 membrane test, one work better than the rest of mine, results better for one than the other. When you pick the scale,
Yeah. For the 5 membranes we tested, the question is there any difference in performance of type 2 and type 3 membranes? Type 2 is peel and stick, and type 3 is the regular membrane. So no, as long as for the 5 membranes we tested, we did not see any difference. There is maybe the type 2 are not as stretchable, so to speak, as the other ones, but that's
Other question is for the product that you guys did. Did you guys use a membrane on that?
yes, we did. That's right. The other question is on the pilot bridge, did we use membrane? And the answer is yes, we did.
So you have recommendation to change specification on the membrane?
The membrane itself seems to be all right. That's what we think. As long as we protect it from abuse, we
How do you
should.
do that? How do you do that?
Good question. Maybe the least we can do is not let the heavy equipment travel on top of the.
But we've got to pave it, right? You need a paver.
Well, I think that's possible, but in some cases, the tops of box beams were fabricated as shards that penetrated the membrane with any kind of weight on top of it. That's fixable. I think if a contractor paves on top of it, if it's adhered well, and if the top of the mat is clean, I think you stand a pretty decent chance of paving on it without destroying the membrane. But I mean, he didn't show you all the pictures, but some of the pictures I saw, they had 50 seconds on top of the membrane. Contractor. We're right across the other side. There was a lack of attention. There was a lack of attention by the administration staff, for sure. It was a local project. But they had full-time inspection.
Right, we also have a question from the computer. What are the effects of vibration during grout curing simulating part with construction study?
So the question is the effect of vibration on the grout. Is that what you're saying? Grout cure. Okay, we did not use any vibration at all. It is just it is flowing concrete almost. So if you see the figure on slide 46, bottom left hand side, you will see the grout workability in the picture. It's really flowable grout. So on the right hand side, the picture shows you the grout inside the recess of the keyway, which is really flowable actually. I think that was very workable. So we did not need vibration. That's the intent actually, because it's very difficult to insert a vibrator into the keyway recess.
So changing shear material and geometry improves the improves the performance of the transfer of the shear. The fundamental question is why are the beams leaking?
Good
Why are the
question.
beams leaking?
That's a good question because so the question is if we change the keyway geometry, we improve the performance. But the fundamental question is why is the joint leaking? So what we have here is I'm on slide 45. On the left hand side, the figure shows in shallow keyway. So we can imagine box beams arranged side by side, and imagine holding the box beams at the top. The beams can rotate and they are unstable because the contact that the keyway joint is giving is only a small amount. So it can truly rotate about the joint actually. On the other hand, if you have deeper keyway, if the bond between the concrete surface and the grout is reasonably good, if it is still intact, that rotation is prevented. That's number one. Number two, the finite element analysis has shown clearly that the stress intensity for deeper joints is significantly smaller than the stress intensity for shallow joints. Therefore, we are reducing the amount of tensile stresses acting on the joint. Number three, we are using higher strength grout. So we are asking for 10,000 psi grout at the time of, until we get 10,000 psi strength, we don't want to use or allow anything on top of the bridge. So that's other part of it. And then number four, the opening itself is so small that really we are not filling the joint adequately, or we don't know if we are filling the joint adequately if the opening is very narrow. If we increase the width, we are increasing the possibility of filling the joint adequately, number one, and consolidating the concrete after placement, which is very, very important.
So I guess, so the answer to Tim's question, are you then saying that the combination of all those movements is in fact then destroying membrane as a possibility?
Yes, the possibility is that, okay, the fundamental behavior is the beams will behave like single units the moment it cracks, the moment the joint cracks. That's what happens. So if we have deeper keyway joint, we are trying to transfer the load over not just one beam, but maybe two or three beams, adjacent beams, because the joint is still intact and it's able to transfer the load between beams. The moment there is a crack and there is the joint has failed, then the transfer of load is not happening and therefore it won't work. So deeper joints will reduce the tensile stresses and therefore the tendency to crack in the first place.
So you went to a bridge that had been in service for 20, 25 years, and they were removing the beams because the beams were pretty much shot. Now, and the intent was that you were going to go out there, the contractor would remove the wearing surface carefully so that you could then examine and remove the membrane that had been placed. Now, you mentioned that in some locations, surprisingly, there was no membrane at all, but you did remove the membrane in other places. What I remember is that you tried to run tests in terms of the properties of that membrane. So what was the condition of the membrane after being in service for 20, 25 years, and how was it different than a new membrane?
The question is, what was the condition of the membrane after the bridge was in service for about 30 years as opposed to new membranes? The membranes that we pulled out from this bridge were in real bad shape. We were able to tear them with bare hands, and they had a lot of holes. So we did not even test those membranes that we recovered from this bridge.
So it's brittle?
Yes, it is brittle. It was brittle, and it had absolutely no strength. So we were able to tear them with bare hands. absolutely, it's quite considerable. And none of our tests relate to long-term performance of the membrane.
So you remember what type of membrane it was?
So we use that in this. All right, I'm gonna put you on the spot. To make these changes on a shear key, we're gonna get leaking joints.
The tendency or the probability of leaking joints is substantially reduced or will be reduced if we increase the depth of the shear key. That's what the that's the findings from our project. But on the other hand, we can also do something else. The something else thing is not in the scope of this project, but let's say the joints actually leak and they can cause corrosion problems. So the box beams themselves can be made more corrosion resistant. Why? Not in this project or not even in ODOT projects, but in other projects we found that if we use polypropylene fiber of 7.5 pounds or something like that, slightly higher dosage, even in structural members, the tendency of the member to see corrosion damage is substantially reduced. So it's by a factor of 2. So we proved that the service life of a reinforced concrete member can be increased by a factor of 2. That means I can double the service life just by adding fiber in the concrete. So these box beams, which are precast beams, so they can easily control the amount of fiber they can use in the bridges, in the beams. So if we add some fiber in there, this type of corrosion damage is likely to be resisted. So we will get, instead of 30 years, we may get 50 years service life or even 60 years service life.
So, so going back to the bridge that you removed the membrane on, the testing that you did was on all of the current membranes that would have like
That's right.
Nothing like a type B.
And the fiber is relatively speaking, inexpensive option. But if I'm able to get 30 more years of life, I think it's worth spending that additional $10,000 or something initially.
The recommendation is you use waterproofing.
I'm sorry.
Is you use waterproofing material then? You're discussing that, it's corrosion resistance.
Once it's corrosion resistant, then the need for waterproofing membrane is somewhat reduced, I would say.
I might ask you a question. So when did we change? Because different types of membranes. We have changed. Like I said, we keep the membranes down. We waste our money putting them down.
You guys understand construction. To pave asphalt on top of the membrane, when you're entering with your paving equipment, puts it on, it's all an aggregate. So you don't have your approaches, your box being prevented. So how you get your toys up there to play is impossible until you say that you can't get it. And then the tack, to say the tack's not cured, the whole put 200-degree asphalt or something, so you can say like it's not trackable. Even the membrane itself, that heat alone of the asphalt, any air that's trapped into waterproofing, which is just like just trying to expand without any normal air into there. And I think that's pretty difficult to construct. That's kind of why I mentioned. That's kind of why I asked that question. I mean, I'm not saying.
Yeah.
We don't put a waterproofing membrane underneath concrete.
That's right.
And right now, our policy is the asphalt wearing surface is a small percentage of where you can put construction. Now, again, we're also talking about a standard that the locals use tremendously. And again, we've done post-tension transversely. We've played around with these joints. I'm not disagreeing with the need for the joint to change. I'm not disagreeing with that. But fundamentally, does it change the outcome? With asphalt wearing surface, does it change the outcome? And that was my question. I don't know if it does. A previous research project indicated that those joints are cracked before you get off the job. Right? Temperature differential, which you place the grout versus the temperature of the boxes. Again, you've got a differential there, you get big heat sink. So you're going to get some shrinkage cracks in there. If these membranes aren't working, we're right back to where we started from.
So you look at temperature movement. How does 10,000 psi hold up to that?
No, we did not look at the grout temperature differential, but we looked at temperature movements of the member itself in the longitudinal direction. And I asked Teddy, and he told me that we don't take care of the differential, the temperature movements in the longitudinal direction.
But are those, do they exceed what we can resist? Do you remember?
I'm not sure, but what's happening is the temperature can cause significant amount of longitudinal movement between adjacent beams. That's a problem, which is one of the causes for cracking the joint. Coming back to your comment, we are not saying the paver cannot be used on top of the waterproofing membrane. What we are saying is, I don't have the picture here. I don't want to, show that to everyone, but I can show it to you later. We observed that the guys are just driving their rollers, truck, everything from one side of the bridge to the other side before the paving is done. That's the problem. Yes, so there is a lot of small aggregates, grid sharp, everything sitting on the bridge. They did not blow it yet, but they are driving their heavy trucks on top of it. It's not the paver. Paver is fine because you're putting asphalt and it's very hard, so you just roll it. That's probably distributing the load over a larger area. Whereas driving a roller on bare membrane with grit or with any aggregate particles will actually make those make the membrane totally porous. That's what is happening. I know. Sorry, Jim. I know. Right.
Obviously, I've been on somewhere they were smart enough to kind of logistically figure out how you could get on one side of the put the asphalt. So we don't want the trucks backing up and forth on the paver on the membrane. So we place it in the paver, and then the paver goes out across the bridge. It's very rare that you have to be on that comment. There's much more to think about, but sometimes to get from one side to the other, it's a long detour.
Right.
So they're going to run the equipment across. It's hard enough to, put the rollers on the one side, the paver on the one, fill the paver up, and then bring the paver out across the deck before you put any equipment on the deck. I've seen it done that way, but that's a smart contractor.
One thing that might help is to inspect the membrane before they actually do the asphalt cut.
Again, we make these changes, we change it.
Yes, a good question. So, certainly, we know that the joints that we have designed fail. We know that the grout.
Sure.
We know that
the grout is shear key configuration. I'm not good at all.
And I think that long term, I think that goes along. It'll be interesting to see how this bridge performs. It's pretty short. I wish we had a longer one. But you asked some good questions, and I guess with a little bit of thought, a little bit of investigation, we might be able to come up with something to address those. But a lot of what we do, and I spend a lot of time. I
And a lot of times I'm out in the field and I really wonder just where our inspection was. Because I just see things that you would never, ever expect to see on a finished product. And so a lot of it has to do with, do we have the, we can solve some of these problems just by adhering to the specifications that we already have without any research. But we just got to pay attention. We got to have the right people out there. So, and that's probably always going to be the case. So even if you come up with this, if you're going to have inspection that's not focused, are you going to still end up with this substandard problem? Maybe.
All right, well, I thank you for your attendance. The recording will be on our website at research here in the next week, and the report should be available in the next couple of weeks. So thank you for your attendance today.
Yeah, it came ready mix. Have you ever done one with a ready mix? You have. Okay. So it was a grout. So I guess one of the questions is how do we come up